then we will have a module on normalization, because often you can have different equivalent databases or relations that represent the same information, that contain in the end the same information, but they differ in certain aspects. Like some variant or some of these relations have more redundancies than others. For example, I show here one relation that I just downloaded from the Finnish Meteorological Institute, which contains temperature recordings. And so this relation has the attributes name, the name of the weather station, then the latitude of the weather station, the longitude of the weather station, a timestamp of the weather recording, when did we take the weather observation, and the value of the observation, of the physical quantity, the temperature. And you see here there's quite some redundancy, because for each recording from this weather station, we always have latitude and longitude. So this here seems highly redundant information. So we could instead have a separate table where we only store apologies. Oh, getting a bit messed up here with my Zoom. So instead of this redundant information, a redundant table, we could have a separate table which only stores the latitude and longitude of each weather station. And here in this table, we only refer to the weather station using its name or some ID. So this will be the core technique to normalize a database, is often to break it into smaller relations that have less redundancy. So I see one question on the chat. The question is, in relational algebra, why would creating a new table be helpful compared to searching in the old table? Yeah, very good question. Well, this is exactly what is done. So you can think of a query or formulating this algebraic expression as formulating the search criteria. So the evaluation of this relational algebra expression is exactly to do the search. So you represent the search, or you encode the search criteria in relational algebra. So this is actually the way you implement the search. And the new table, you can think of the new table as the temporary results of the search. This is the results that the search delivers. Yes, any other questions? Do not hesitate to post them on Zoom or in Slack. Okay, so normalization is important to avoid redundancy, and also it typically prevents mistakes. Think about we correct the latitude and longitude of this weather station because the original latitude and longitude was erroneous. We made we had a GPS measurement error. So once we have now a new latitude and longitude, we would need to replace all these entries in this table. And if we miss one of these rows, we would have inconsistent data. So we would have all of a sudden two rows with the same weather station, but at different locations, which doesn't make much sense. And when we normalize this database, so we avoid this redundancy, we also minimize or we reduce the risk of such update anomalies or errors. And you will learn how to implement such database normalization in module 3. Okay, then the fourth module will be on indexing, also an important topic for databases. And yeah, as the name already hints at, and maybe you have came across this before, an index is like for a book. So here I am currently working on a dictionary of machine learning. And you can think of this dictionary as a database. So each entry in this dictionary is one tuple in this database. And to search a certain term, let's say the term data, you could browse through this dictionary one page after the other until you find it, or you use the index. So you look up in the index for data, well, it's not here, but let's say you want to know cluster. Okay, here is the index term cluster. It's at page 22. And similar, we use an index for databases. In databases, we want to look up a certain entry or a certain tuple based on a given identifier. Like here, the identifier is the index name or term cluster, and the index then shows us where this database entry or this tuple is stored in memory. Like here, it's the memory is the PDF, or if you print out the pile of pages, is the memory, and the index tells you on which page can you find the entry for cluster. Okay, and the last module 5 will be on transactions, which is then a bit more advanced because we now need to take into account the implementation of a database. So a database or a database system, database management system, often must serve more than one user. And it's actually, I mean, I cannot think of a database system that only serves one single user. If you come up with one application, please let me know. So it's almost useless to have a database system that only works if there's only one user working on this database. So you will have concurrency. You will have a system, for example, a database system. I could mean a web server application. So you develop a Python code that runs on a web server which has this IP address, and this Python code manages the database. For example, it processes user requests, and here I have shown two code snippets in Python that could actually implement such user requests. So you have here user one, which formulates a query. So this is this SQL language that you see here, and you will learn it also during this course. You will learn how to use this SQL language within Python. So you will actually learn at least two new languages in this course. You will learn SQL, you will learn Python, and actually, strictly speaking, you will also learn a third language, relational algebra. So this course is essentially teaching you a lot of languages. And yeah, so you use here this SQL query to implement or to set up a request. And this request can be implemented in a lower level, for example, by IP sockets, so by some lower level technology, which is not really relevant here. But at any time, and this can be arbitrary, can be exactly at the same time another user also accesses this web server that manages the database. So what happens if they access the same element of the same table in the same time, and one of them writes or changes, modifies this entry? So let's say one user one, changes the information for the cow Zenzi, and the other user also changes this information for the cow Zenzi. And what happens if they modify this tuple not at once but step by step? So user one starts to rewrite this tuple while user two is still working on it. And this results in what is called conflicts, and we want to, of course, minimize these conflicts. And one way to minimize conflicts is using so-called transactions. So these transactions is a mechanism to make sure that once a user starts to write a tuple, it's blocked for any other user. So you cannot, these users cannot override each other's requests to some extent. And you will learn how to implement simple form of transactions also in module 5.